All right, so yeah, the next speaker is Muhammed Sayin, who is an assistant professor right now at Bilkent University in Turkey. And so he's going to tell us about his work on fictitious play in Markov games with a single controller. So yeah, take it away.
Hello, everyone. Thank you for the introduction. This is a joint work with Kaiqing, Zhang, and Asuman Ozdaglar from MIT. And we all know game theory has a prediction power to understand how intelligent decision maker interacts with each other, right? But what is the prediction power of game theory? Can we quantify that? Because empirically, it has been observed that if human-like decision makers interact with each other in a repeated game setting and receive feedback from the environment, they will eventually converge to some equilibrium, right? This has been observed empirically, and terrific network is one of the examples. Researchers back in 90s, in early 2000s, studied this problem to come up with some theoretical learning models, some behavioral heuristics explaining that kind of phenomena. And one of the popular one is the fictitious play. This is a very simple heuristic, right? For example, suppose that we are playing rock, paper, scissors game. In this game, we will model the opponent as playing some stationary strategy, saying which action should be played with what probability. Then we will form a belief about that stationary strategy, even though that is not a correct assumption, and based on our observations. For example, if in the past of the play, if the opponent played 50% of the time rock, then we will think that maybe with 50% probability, the opponent playing rock. Then we will take the expected, we will take the greedy best response to maximize our expected payoff, given our belief. This is a well-established subject, especially in the repeated game setting. We know that given the spectrum of games from the fully competitive two-player setting to the aligned objective multiplayer identical interest settings, we have convergence, meaning that the beliefs formed will converge to some equilibrium. Right? This is well established. We also know that fictitious play will not converge all the time. Right? There exist some special classes of games in which fictitious play cannot converge to an equilibrium. But even though those are all well-established results, they are all limited to the repeated game settings. Right? On the other hand, recently a new phenomena is emerging, like AI systems. We have seen many applications of RL from social life to the digital economy. For example, human-AI interactions, autonomous systems. And the interest of this conference, we have seen many talks in which we applied AI to some digitalized economy applications, from auctions to pricing. For example, they applied Q-learning to that with independent agents. But you can remember in one of the talks, plenary talks, they mentioned that when they applied Q-learning to these applications, sometimes they cycle, sometimes they converge. This has been observed empirically. The question is, can we come up with some theoretical guarantees for that kind of problem so that we can design more reliable mechanisms, right? And therefore, even though fictitious play has been studied back in the 90s, and we have some well-established results, I believe that it is the time to revisit fictitious play or learning in games to address this new phenomena. In it, we have an advantage here, because back in the days, we were trying to model humans, right? It is very difficult to model humans. Like, how do they make a decision? They can act unreasonable sometimes. On the other hand, AI systems will be designed to maximize some objective function, right? We have an explicit objective there. On the other hand, AI systems do not have feelings. They will act more reasonable, more rational. And that's the advantage we will have. In that case, the models we formulate, will lead to more reliable outcomes for us. To obtain some explicit results with wide range of applications, we will focus on Markov games. And Markov games is a generalization of Markov decision processes to multi-agent settings. And Markov decision processes is the basis for reinforcement learning. In that respect, Markov games will be an ideal model for multi-agent reinforcement learning. And the model is like this. We have multiple decision makers. We will denote the typical agent as I, and there are n players. We have a multi-state environment, and the state will be denoted by S. The state of the environment will change depending on the current state and the current action profile of players. Right? It will depend on everyone's action. And that will be depending on that state transition probability function. On the other hand, players will also collect some reward from the environment, and that reward will also depend on the current state and current action profile. And their individual objective is to maximize the discounted sum of the rewards collected over infinite horizon. Right? But today, we will specifically focus on the Markov games with single controller. The difference is state transition probabilities will depend on only a single agent's action. Right? You can, as an example, you can think this one as maybe we have a hierarchically higher level player, such as a government, which can have more deterministic role on the state of the world. OK, what is the counterpart of the classical fictitious play for Markov games? And we will address this question by making a comparison between repeated games and Markov game setting. In the repeated game, suppose we are playing rock, paper, scissors repeatedly over discrete time. That will look like that. On the other hand, in the Markov games, there will be multiple states of the world. In different states of the world, we will be playing different games. For example, in one of them, we can play rock, paper, scissors. In another one, we will be playing matching pennies. And the state of the world will change in time depending on our actions. If it doesn't depend on our action, then it will be more like we are playing repeated games interleaved with each other, such that we can follow some fictitious play in parallel specific to every state. On the other hand, since the player's action determines the next state, now players face a trade-off between immediate stage payoff and the continuation payoff. Why? Because some of the states might be more preferable for the players compared to the others. And now they need to decide whether they would like to get the immediate stage payoff or they would like to transition to a better state. Right? And also, the continuation payoff will depend on their play in the future. This is ambiguous, how they are going to play. A standard assumption is they will play in the future as they play today. And based on that, we can model the continuation payoff and construct an auxiliary stage game which incorporates the immediate stage payoff and the continuation payoff together. And we will call that Q function. This is also a very standard definition. But the issue here is the Q function, since it depends on the player's strategies, will change in time. Because opponent is adapting. Because of that adaptation, we no longer have a stationary game. Right? The game will be non-stationary. This is not exactly the repeated play of the same game. And more explicitly, the fictitious play dynamic we will present will look like that. In the classical version, again, we assume that the opponent plays some stationary strategy, and we form a belief and take the greedy best response to maximize the expected payoff. In the Markov game version, again, we will do the same thing, but now we are forming a belief specific to every state for the opponent's strategy. And we are also going to form a belief about the continuation payoff based on our observations. OK, and more explicitly, the mathematical formulation of the dynamic will look like this. I am explaining this over the perspective of player A. And specifically, if state S gets visited, player A will form a belief pi for the opponent's strategy, Q for its own individual Q function. Now, given those beliefs, he will always take the greedy best response to maximize the expected payoff in the auxiliary stage game. And you can see this at the first step. And there might be multiple maximizers. He can use any tie-breaking rule. Now, the opponent will also do the same. Therefore, player will be able to observe the opponent action. Given the observation, now the player will update his belief. And the update will be the convex combination of the current belief and the new observation. Now, you can view the action as a probability vector, which gives a probability 1 to the action taken and 0 to the other. Now, and alpha k is some step size. Like the first part, as you see, the steps above the dashed line are exactly the classical fictitious play. Now we have added an additional step, which is the update of Q function estimate. And that update will be the convex combination of the current belief and the realization, which is the Q hat. And the Q hat is exactly the RA, which is the immediate stage payoff plus the discounted continuation payoff. That green term is the expected value of the next state. And the expectation is taken with respect to the state transition probabilities. And the value of the state is exactly the value that player takes by taking the greedy best response given his beliefs. Right? Now, as you can see, we use two different step sizes, alpha k and beta k. The reason is, if beta k goes to 0 faster than alpha k, in the classical fictitious play part of the dynamic, it will be almost like they are playing a repeated game. Right? This will give them a chance to track an equilibrium associated with the with their belief on Q function. And this is also a kind of reasonable because Q function is essentially the payoff for the auxiliary stage game, and payoff is more like a preference. From that perspective, our preferences change more slowly compared to our choices. Since they change more slowly, we can use smaller step size to learn them better and better in time. On the other hand, choices, especially the opponent strategy, can shift in time. To be able to track that kind of shifts, we will use larger step sizes. And this is the formal result. Given a Markov game with single controller, we will have convergence in two-player zero-sum setting and multiplayer identical interest setting, given that the step sizes satisfy this 2x scale learning assumption, which is beta k goes to 0 faster than alpha k. And this is an almost sure convergence result. We also have a corollary to that. The corollary says that in Markov games with single controller, if the stage payoff of non-controller players satisfy this condition in comparison to the stage payoff of the controller player, then we also have almost sure convergence. And this structure is like potential game-like structure, meaning that given there exists some potential function for non-controller players' stage payoff, and that potential function is aligned with the stage payoff of the controller player, then we have convergence. And recently, we have seen many definitions of Markov potential games, and they mainly focused on the utility, total discounted sum of the rewards. On the other hand, here we are considering some definitions specific to the stage-wise interactions, and this is only about the immediate stage payoff, and this is thanks to the single controller assumption. And I would like to give a sketch of the proof for starting with the zero-sum case. In the zero-sum case, we are assuming that the immediate stage payoffs sum to 0. And in the above, you will see the discrete time update specific to state S. But for each state, we will have that kind of dynamics. And those dynamics are, coupled with each other because of that the continuation payoff, right? On the other hand, we can analyze this discrete time update by using some continuous time approximation. Thanks to that 2x scale learning assumption, now, as you can see, time derivative of Q is 0, meaning that the continuous time version is exactly the continuous time best response dynamics in a normal form game. But this is not exactly a zero-sum game. Why? Because players keep track of their Q function estimates individually. They don't have a common estimate. Because of that, even though the underlying game is zero-sum, it is no longer a zero-sum. It is a general-sum game. But the issue is, in general-sum games, best response dynamics do not necessarily converge to some equilibrium. But we come up with some Lyapunov function such that we can quantify the sum of the value functions in terms of the sum of Q functions, such that we can show asymptotically they will become zero-sum. Given that, we can show value function estimates track the min-max value. And given that tracking result, now the Q function iteration will look something like that. And that term is almost like a Bellman operator with some asymptotically negligible error, because max-min is also a non-expansive function. And therefore, we have some contraction property from here. Because of that contraction property, the proof will follow. On the other hand, in the identical interest case, it is more challenging. Why? We can, again, follow the same steps. Again, the time derivative of the Q will be 0. But the issue is, will it also become identical interest in time, asymptotically? If it is becoming identical interest in time, will it also track some Nash equilibrium? If it is going to track some Nash equilibrium, which value it will take? Because in the zero-sum games, even though there might be multiple equilibria, all of them will lead to the same value, right? Min-max value. On the other hand, in the identical interest, there will be multiple values. Suppose we have also selected, we know which value it will track. Now, the fixed point iteration will look something like that, but now we don't have a contraction property. As mentioned in one of the plenary talks on min-field games, analyzing the convergence properties of a fixed point iteration without contraction property is quite challenging. And the solution we come up with is based on monotonicity idea. Right? Let's focus on the continuous time dynamics for the identical interest game. In this game, we can show that we will have some kind of monotonicity for the value of the game. Right? Given that monotonicity in the continuous time, let's also suppose that in discrete time we also have some monotonicity. Okay, let's also suppose that we also have some monotonicity. In that case, the discrete time update will be also monotonically non-decreasing. Since it is bounded from above, it will converge. But this is just in the continuous time. In the discrete time, there will be perturbation. We will have some monotonicity error. To be able to address that, we will specifically focus on the incremental part and come up with some Cauchy sequence type of convergence, but from one side only. Right? We are mainly interested in non-negativity of the increments. And if we can show this, we are done. To be able to show this, we will specifically focus on the evolution of the gamma k instead of qk. But it is very challenging, right? Therefore, we are only interested in one side. We are interested in whether there exists a lower bound or not. And the single controller condition will make the game strategically equivalent to some identical payoff game such that some complicated term in the evolution of gamma k will be lower bounded by 0, and we can simply ignore them. Because of that, now we can come up with some lower bound on its evolution. Some Gromwell-Lemmel type of argument will help us to find a lower bound on gamma, and we will be able to show this. Well, what are the key takeaways? Firstly, it is the time to revisit the theory of learning in games, because now AI interactions becoming a new phenomena, or RL, multi-agent reinforcement learning. And today we have presented the two-time scale learning framework, which establishes a bridge between learning in games and reinforcement learning. And we know that those are very rich areas. Because of that, this framework, we can marry many different approaches from these fields together, and that will lead many interesting future research directions. And if you have any questions or comments, you can always reach me via this email address. This is my last name, .ee.bilkent. And for the appearance of the papers or related works, you can check my lab webpage. Thank you.
Thanks a lot. Yeah, so let's once again take 2 minutes for questions. I actually also had a question about your, so about the model. So you have like basically these two parameters are alpha k and beta k, but so are you kind of like then assuming that like every single agent in the game is then going to have the same parameter?
Yes, in this paper we do, but we have a follow-up paper in which we relax that assumption. They can use different step sizes as long as individual level they form that two-time scale learning assumption.
I see.
They satisfy. We will still have some convergence given some condition over the discount factor, because in that case, the deviation from the zero-sum structure or identical interest structure will be a lot. Right? Somehow we need to restrain that, and discount factor will help that.
I see, nice. And so like technically they don't really have to coordinate in advance on like what their rate is going to be then.
Yes.
They could just like have different rates. Okay,
yes.
Nice. Thanks. Anyone else have any question?
Also, there's no question in the chat. Yep.
Okay, well,
okay,
then thanks again for the great talk. And so then we'll have the next speaker, and the last talk of the session.